So this is fourth talk of this foundational course on group theory. Will be taken by Saheb Mohapatra of second year B.Math. Over to you, Saheb.
Okay, thanks. And am I audible to everyone?
Yeah.
Yes.
Okay. Okay, and I'm sharing my screen. Is the screen visible?
Yeah.
Yeah.
Okay. 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 Nice. Okay. So in today's talk, as mentioned in the email, I have to cover group actions and conjugacy in groups. But to start with, I pose this question that you can see in the board. If you have a cube and you have n colors, how many distinct colorings do you have? By distinct, I mean, suppose you have a coloring of a cube, and if you rotate it and you get a different coloring, so those two are same. So in that sense, I ask how many distinct colorings can you form if you have a cube and n colors? And this is a combinatorial question which can be answered using the very basic ideas of combinatorics. But today we'll develop some group theory techniques and some results that can be used to find a simpler way to solve this question, and furthermore, more difficult and complicated questions related to combinatorics. So to reach there, we need some definitions and some results. And we'll start with group actions that was introduced, I think, in the first talk. Suppose you have a group. I think it is working. Yeah. Suppose you have a group G and a set A. It is just a normal set. It did not have any particular features as you have in a group. Then a group action is a map from G cross A to A, satisfying two things. One is the identity times A is A for all A. And if you have G1 and G2 belongs to G, then G1 times G2 times A, and G2 times A belongs to A because it is G cross A to A, is G1 G2 times A. And G1 G2 is here the product that is defined in the group itself. And this dot represents the product that we define while defining an action. And this is not unique. Like for a particular group and a particular set, we may have several actions. One very trivial example is to give an action that has of this type, like for all G dot A equals A. This is also an action you can check it satisfies all the criteria. But this is a very trivial action, and we can have several different actions for a particular group A, group G, and a set A. So is the definition clear to everyone?
Yes.
Okay. So to get an idea of what the group action does, you can see that if we have a element G from a group and we keep on multiplying G by A, all the A's in the A, then we in some way shuffle the elements in A. Means it's kind of a permutation of the set A. So the word permutation means it has to be a bijective function from A to A, but means it is clear that it's bijective because suppose we have a element G and we keep on multiplying with A. Then suppose we have two elements from A, say A and B. Then if we have GA equals GB, we can multiply G inverse, right? G inverse, and we get A equals B. So it clearly shows that this is 1, 1. I mean, if you take two different elements, you get different results. And if you have any element A in A, then G inverse A belongs to A, right? Because G inverse belongs to G and G cross A to A is the map. Now G of G inverse A is A. So for every element A, we get a pre-image G inverse A, and G as well. So G of G inverse is A, so it is on 2. So G behaves as a function, as a bijective function from A to A. So it seems that there is some relation between this group G, means the elements of the group G, and the set of all bijective functions. Bijective functions from A to A. I hope you can see how every element does something that is similar to a bijective function. And okay. Okay. So have you guys ever seen this notation SA for some set A?
Yes, this was there in the last lecture.
Okay. So what do you mean by SA? Could you explain?
It's the set of all bijections from A to A.
Right. So need this set be finite or infinite? This SA can be. I'm asking, can this set be finite, or can it be infinite, or what are the possibilities?
When it is finite, we get Sn.
Right. And it can also be infinite, depending on the set A, right? Because number of bijective functions can be infinite. If you have an infinite set, you can easily construct. Can anyone give an example of that? You can take any infinite set and
Sir,
try
can you
to.
repeat the question?
The question is, if we have A infinite, give me an example where SA is infinite. Or is it always true?
Another enumeration of the natural numbers.
Right. You can take the
Or
natural
even
numbers
real
and
numbers.
yeah, it's a very trivial thing what I'm talking about. Fine. So what I was telling in the last slide is that this SA has some relationship with G, right? Because every element in G does some permutation of the elements in A, and we'll come back to this after going after some time. After we define some other things, we'll come back to this. But now, suppose we have an action from G cross A to A, and we say that A related to B means AB belongs to A, B belongs to A, and A is related to B if and only if A equals G times B for some G belongs to G. We can define a relation between the elements in A, and it is very clear that this relation is equivalence relation because A is related to A if G equals 1. We can take G equals 1 and show that A is related to A. And if A is related to B, then A equals GB implies G inverse of A equals B. So B is some G inverse times A, and G inverse belongs to the group G. So again, B is related to A. And if A is related to B and B is related to C, then A equals G1B and B equals some G2C. And then you can show that A equals G1, G2 of C. And G1, G2 belongs to the group because the group is closed. So every time we get an equivalence relation, what do we get? Can anyone say? What is the most direct thing that we can associate with an equivalence relation?
A partition.
Right. So but why do we need a partition here? Because the whole purpose of doing all this thing is to study more about this set A, and to use that information to study about the groups. Means in both ways we can do those things. If we know about groups, then we'll know about the set A. If we know about the set A, we'll again have the information about the group G. So this equivalence relation gives us a partition of the set A. And suppose we have an okay suppose we have an element A belongs to A, then I write GA as the set defined by G belongs to G. So this is the equivalence class of A. I mean, all the elements of G will keep on multiplying, and we get some different elements in A, and that set we call the equivalence class of A. Means all those elements are related to A in by some G. I mean, if we write GA, we can again write G inverses. So it's the same thing of writing GA here. And this thing is called the orbit of A. The orbit of A is this set, and like it's like having an element A, and we keep on multiplying something, then we reach some element B. We may stay at A, obviously, that is also a possibility. And it's like a path covered as we keep on multiplying different elements from G. Maybe that's why this name orbit. Okay, we'll keep on defining further new things. As I have said in the last slide, that if we keep on multiplying G with A, we may end up with A. What is the most trivial example? What is the most trivial example of having GA is A, G dot A is A? Means which G does that?
Identity.
Identity.
Yes, the identity does that. But is it any restriction that only identity has to do that? There can be a possibility that more than one element fixes A. This is fixing A, right? So one simple example, consider the equilateral triangle. I mean, the vertices of the equilateral triangle, 1, 2, and 3. And have you guys heard of the dihedral group?
Yes.
Yes. So can anyone give me an example of, you can see that dihedral group acts on this triangle, right? The reflection about, say, this axis and the rotation up by 120 degrees. Can anyone give me an example of more than one element fixing, say, this vertex?
The reflection about this fixes this vertex.
Yes, the reflection fixes this, and the identity element obviously fixes this. In fact, about every, I mean, even for this also you get two elements, for this also you get two elements. So clearly we can see that even in small groups also we are getting examples of that. So we also have defined a term for that. That is called the stabilizer of X. Stabilizer of A is all those G belongs to G such that G dot A equals A. And so you can see that stabilizer is a subset of G, right? So what is more useful is that if we get it to be a subgroup of G, and in fact, if you try to prove, you can see that it is a subgroup of G, like E belongs to stabilizer. And if G1 and G2 belongs to stabilizer, then G1A equals A, then you multiply G2 on both sides, then G2, G1, A equals G2A equal, and G2A is A because it belongs to stabilizer. So even inverse also you can do the same thing. And we prove that stabilizer of A for every element A is in fact a subgroup of G. Why do we need this? Because using subgroups, we have already proved some theorems like the Lagrange's theorem, and we can effectively use that to count some things, which we'll be doing next, I think. Okay, then I think we have defined the stabilizer, then we have defined the orbit. Okay. One more thing is that, do you see the analogous thing of stabilizer? Like stabilizer is a subgroup of G, and it fixes, for every element we get a stabilizer. Similarly, we can define the other way, like for any G, consider all those elements that G fixes, like X such that Gx equals X. There can be a set like this, right? If we take any G and we find all those X in the set A, and we collect all those things that G fixes, and that we call the fix of G. And this is a subset of A. We can't add more things, more than subset, because we don't know what A is. A is normally is normal, just a set and nothing, no structure to it. So fix sub G and stab of A are two analogous things. And one thing we can notice, I don't know how trivial it is, but summation of stabilizer of A belongs to A, is equal to summation of fix of G belongs to G. Okay, how many of you can see this being true? I mean, is this trivial, or has anyone any idea of proving this?
By
Any
summation,
techniques?
you mean union?
No, okay, sorry, I need to write this. This is the cardinality. I'm sorry about that. This is the cardinality of the set.
Sir, we can consider all the pairs A and G for which stabilization is occurred, and the first one just counts the G's and then sums over A's, and the second one just counts the A's and sums over G's. So
Absolutely,
this
very
is the
nice.
same thing.
Exactly. So I'm just writing it what he said. We take this set S, and S is G comma A, with this GA condition is GA equals A, and we count it in both ways. Like we can fix a G and we can count all those A's it fixes. Like we fix some G and we count fix G, the set fix G, and we find the cardinality. Means we find all those A that this G fixes, and then we sum over all G. And the same thing can be done in the reverse way. We fix some A and then find the stabilizer of that A, and then we sum over all A. Like we find the stabilizer of that A and we sum over all A. So that result is clear, that sum of stab A cardinality is sum of fix G. Okay. So this is very useful and will be required at some point. Another thing that we need to see is called the orbit stabilizer theorem. So I have defined orbits and I have defined the stabilizers. But let us do one thing. So let us consider an element A and say G1A equals B and G2A also equals B. What can we imply from that? We can say that G2 inverse G1A equals A. So this thing, this G2 inverse G1, belongs to the stabilizer of A, right? G2 inverse G1 belongs to stabilizer of A. And this stabilizer of A is a subgroup of G. So G1 stabilizer of A equals G2 stabilizer of A. Okay, so you people know about cosets, right?
Yeah.
So stabilizer is a subgroup and it will have cosets in that cosets will partition G, and then if we have G2 inverse G1 belongs to stabilizer, then G1 stabilizer equals G2 stabilizer. These two cosets are same. So you are clear with this? I mean, any doubt with this step? Okay, so I'm moving on. So what we get is that if we have some element B, say not equal to A, then that all the possible ways of getting to B, I mean, if G1, G2, G3, suppose say up to Gn multiplied with A give B, then all these belong to the same coset, right? G1 stabilizer A equals dot 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 is Gn stabilizer X A. So if we have any different cosets, then we will not get B. We get any different element C. what do we get if we have stab A? If we take any element from the stabilizer and then we multiply it with A, then we get A, right? So for stab A, we get A. Say for some G1 stab A, we get, say, B. And so on up to, say, some Gn. All this G1 to Gn, these are all different cosets. Otherwise, we'll never get different elements. We get, say, any other letter, say K. So these all things, these A, B up to K, these are all the elements in the equivalence class of A. These all belong to the equivalence class of A. And what do we call the equivalence class of A? The orbit of A. And we see that the cardinality of this is same as the number of different cosets. I mean the number of cosets, no need of saying different, the number of cosets. And this number of cosets, as you know, is the index of the subgroup, that is G stab. And can anyone say me the Lagrange's theorem, if you have studied this in these sessions?
The order of a subgroup H divides the order of the group G.
Yes, and order of group G equals order of this subgroup times its index. Right. And we have just seen that this thing, this index, the number of cosets, is same as the cardinality of the orbit. So we can say that this is stabilizer of A times the orbit. And this is the orbit stabilizer theorem. So has everyone understood it, or anything you want me to repeat in this?
It's okay.
Okay,
Can you go
very
through
nice.
the proof once more?
Okay, fine. So you mean this thing, this proof, that index and orbit, right?
Yeah.
Okay. So one thing is that every element of the group G that belong. Okay, one thing you know that these elements of the group are partitioned into this, right? These cosets.
Yeah.
Okay. 1 minute. Something happened. Yes. Yeah. So if we take, suppose we have elements in the group, right? So we can take that element from the stabilizer. We can take that from any other coset. Suppose we take from the stabilizer and we act it on A, then we get A, because that's how we have defined stabilizers. If we take from any coset of the stabilizer, we get B. And we have seen in the previous slide that if we take from a distinct coset, we get a different element. Like B can be achieved only through one coset. Any other element can be achieved through any other distinct coset. So there is a bijective correspondence between that. Any element in the orbit has a distinct coset from which it has come from. Right.
Yeah. Got it. Thanks.
So if we find a number of cosets here, we are indirectly counting the same thing. We are counting the number of distinct elements, because if you take a distinct element, we will get a distinct coset. And if you take a distinct coset, obviously the element that you get is the unique element from that coset. Like suppose, okay, so wait, yeah. Suppose we take G1 times some G1 stab A, this coset, let it act on A. When I say this coset is acting on A, means for every element I am checking and finding what is the result. Then some G1, say HA, and this H belongs to this stabilizer. Then HA will be A, right? So G1A, as I have defined, is B, then we'll get B. So from this side, we are always getting the same element. And if we have G1A and G2A giving the same result B, then G2 inverse G1 belongs to the stabilizer. And as you have seen earlier in cosets, if G2 inverse G1 belongs to the same, belongs to a subgroup, then G1 times the subgroup equals G2 times the subgroup. I mean, these two are the same cosets. Okay, so what we have got is that the order of a group is order of stabilizer for into the orbit order of the orbit, and for every element A belongs to set A if we have an action. So we have to keep this in mind because we'll be proving something next, and this should be used there along with the theorem that we proved previously. Okay. So up to now, we have proved that sum of stabilizer of A, or sum over A, I mean the cardinality of stabilizers, is sum of G belongs to G fix of G. And this is orbit A times stabilize A. Now, one thing you can notice that in this summation, this stabilizer of A belongs to A. And we have already partitioned A, right? We have partitioned A into distinct orbits. Say this is the set A, and we have partitioned it into some orbits. So if we say A belongs to A and we sum over A, then it is same as summing over A in one orbit and then going to the next orbit and then going to the next orbit and so on, and covering all the orbits. So this thing can be written as sum over I equals 1 to, suppose, say K, sum over A belongs to orbit, ith orbit, that is OI, stabilizer of A. So one thing to note here is I have used K here. I mean, I am assuming everything is finite, and everything that I have done till now, we are in the finite setup. We are assuming we are in the finite setup. So because we are doing mostly counting things, and we'll be applying it to the counting question that I have posed. So is it clear to everyone this this equation here?
Yeah.
Right. So we can partition A into orbits, and then we can just sum over each orbit, then sum over orbits. And note that this inside this thing, if A belongs to orbit, ith orbit, then A is an element of this orbit, then we can say this is the orbit of A, because I mean, if A belongs to this, A cannot belong to any other orbit because we have partitioned it. All the partitions are disjoint. And if A belongs to this, then A, B, like this, we can get C, and we get, this is the orbit OI. And stabilizer of, say, any other element apart from A, say B, I claim that this stabilizer is this set G stabilizer A G inverse, where B equals G. So I'll be proving this, and then only we'll be able to simplify this double summation. Okay. So say B equals GA. So I have said that that is the stabilizer of B. So we'll prove both inclusions. Let H belongs to stabilizer of B. Then HB is B, and we can write B equals GA. Then HGA equals GA implies G inverse HG A equals A. So this implies G inverse HG belongs to the stabilizer of A. And if this happens, then H belongs to G stabilizer of A G inverse. So this one you can see, right? I mean, is everyone convinced with this?
Yes.
Yeah.
Okay, nice. So the other other inclusion is that if, let's go backwards from here only. If H belongs to G stabilizer of A G inverse, then we get this GH inverse belongs to stabilizer of A. Then GH in G inverse HG of A is A. and then we get Hg equal to J. Exactly going backwards, we get that H belongs to stabilizer of B. So we prove both inclusions and we get that stabilizer of P is this set, G stabilizer of A, G inverse. One thing to note here is that the cardinality of stabilizer of A is same as the cardinality of G stabilizer of A, G inverse. So why is this? You can draw bijection from to prove cardinality is same. You have to draw bijections, and if you take any element, say H belongs to stabilizer of A, and you map it to say G H G inverse. This G is fixed for some G, and I mean if you vary G, then this result will be true for all G. I mean in this case it is fixed, and you can prove that this is a bijection from this set to this set, and these two have the same cardinality. In fact, for any subgroup H of G, GH, G inverse has the same cardinality as H. One thing you will tell me is, suppose H is a subgroup. Is this a subgroup?
It's a subgroup only when H is normal.
It's a subgroup only when H is normal. If H is normal, then this is H, right?
Oh,
It is
yeah,
a
sorry.
subgroup
sorry.
irrespective
I
of
don't think
H is
it's
normal.
always a subgroup because the G inverse and G cancels out if you take two elements. I think so.
How does it cancel out?
No, if we take two elements GH1 G inverse and GH2 G inverse, then the result we get is GH1 H2 G inverse, which is also in this left hand set because of the
Right,
closure of
right,
H.
right. And anyone else was saying something, I think. I could not hear that one.
I was just saying that it is a subgroup irrespective of H is normal or not.
Right. So people are convinced with this, and we'll come back to something similar to this later. So we have got that stabilizer of B is same has the same cardinality of G stabilizer of A G inverse, and stabilizer of A has. So this means stabilizer of A has the same cardinality as stabilizer of B for all B belongs to orbit of A. And here I have written orbit of I, if you remember in the last slide. I mean, I is just a notation. Okay. So what we had in the summation was this stabilizer of A belongs to A equals summation I equals 1 to say K, and A belongs to OI stabilizer of A. So in this place, I mean, in the place of cardinality of stabilizer of A, if we keep on varying A and if we remain in the same orbit, so we'll get the same cardinality, right? As we have proved in the previous step. So we can proceed to write stabilizer of A times this sum over all the elements in O means that is the cardinality of OI, that is cardinality of OI, which is the same as orbit of orbit of A. So can anyone quickly suggest the next step?
This is just order of G.
Exactly. So by the orbit stabilizer theorem, this is stabilizer of A into orbit of A. So this is order of G, and we can remove the summation equal 1 to K of 1. This is K times G. K times order of G. What is K here?
The number of orbits.
Right. So this result gives us that we can get the number of orbits, we can find the number of orbits to be the sum of And we have this data, this same sum of sub G. The quantity of G. This is a very useful result, and we'll apply this to solve the cube problem that I posed in the beginning. Okay, so the question was, you have a cube, and if you have n colors, and the question is, you color a cube. So what are the number of possible colorings? Means all possible colorings. What is the number of that? We color the face. I'm asking, what is the total number of colorings that we can get? Need not be distinct. All possible colorings. We have 6 faces and we have n colors, n different colors, and we can use anything anytime. There is no restriction on that.
N to the 6.
Yes, obviously, it's a very simple thing I was asking. It is n to the power 6, but clearly, many of them are not distinct. Okay, suppose let there be 2 colors, white and black, and can anyone give me an example of 2 differently counted things? I mean, in n to the power 6, we're counting everything is different, so we're counting everything one time. Give me an example of a cube that where we have 2 colors, white and black, and 2 colorings which are not distinct. If we rotate it.
So if you have all the colorings as white and one black, then we can choose any particular black corner, but they're the same thing up to rotation.
Okay. You mean black face?
Okay, so one face is let the front face be black and all the other faces are white, and another one where the back face is black and all the other faces are white, but they are the same thing, right? Up to rotation.
Right. Yes, exactly. So our purpose is to count all the distinct ones, and we will use something that we proved just now, the previous theorem. Actually, we'll prove it. We'll use it to find the number of distinct things. So, what are all the possible rotations we can have in a cube? Like if we have a cube, and this top face and this bottom face, say we have an axis passing through this perpendicular axis. We can rotate about this axis, and we can rotate by 90 degrees, 180 degrees, and 270 degrees, and 360 degrees. And with 360, we'll get back to the same configuration that we have begun with. So this is, let us name it by rotation, say 1. One more type of rotation is like this. Take this edge and this edge, and holding these 2 edges, rotate it by 180 degrees. So let us name it rotation 2, say. And you can observe one thing in this rotation. If we hold these 2 edges are basically obtained if you have 2 faces intersecting, right? Like this edge is obtained by this top face and the backward face intersecting. And if we rotate it by 180 degree, what happens is that these 2 faces interchange their faces. And these 2 faces, similarly for this edge, right? So for this edge, this top face and the back face interchange. And for this edge, this front face and the bottom face interchange. Is this clear to all? Otherwise, I repeat. If you want me to repeat, you can say. Otherwise, I'll move on to the next rotation. Okay. So I got logged out, I think. Yeah. So where was I when I got logged out?
Can you explain the last diagram once again? The audio and video was chopping off at that time. It was a bit difficult.
Yes, yes, yes. But which one? You mean the rotation 2?
Yes, the second one.
Yeah. So in this type of rotation, we take two edges and say this edge and this edge. I mean, they're kind of a diagonally opposite, and we hold these two edges and rotate it by 180 degrees. I mean, like this, somewhere like this. So what happens is that I'm drawing a bigger diagram. Otherwise, it's difficult to explain. Okay, say this top face is 1 and say 1 then 6 and this is okay. This front face is say 5 and this back face is say 2. So if we hold this edge and this edge and rotate, what happens is that this 1 and 2 interchange their places and this 5 and 6 interchange their places. 5 is not this one, 5 is the front one, I mean this face. 5 is this face and 6 is this face. So what is happening basically is that if we have an edge, then we have two faces intersecting, right? Like if two faces intersect, we get an edge. And if we rotate about that edge, then those two faces exchange their places after 180 degrees. That is basically happening here. And if you rotate by 360 degrees, we get back. So there are two possible things here. So is it clear now?
Thanks, it's clear now.
Okay. So one more way of rotating is having a cube and taking the main diagonal and rotating by 120 degrees, 240 degrees, and then 360 degrees. So to visualize it, say this corner is formed by intersection of three faces. This three adjacent faces. These three adjacent faces intersect and form a corner. Similarly for this corner. So when we rotate by 120 degrees, it is like moving the three faces like similar to moving this triangle, right? If we have 1, 2, and 3, and if we rotate by 120 degrees, 1 goes to 2, 2 goes to 3, and 3 goes to 1. The same thing here happens. Like we have three faces, three adjacent faces forming this corner. And if you rotate by 120 degrees, say this face 1 takes the place of face 2, face 2 takes the place of face 3, and face 3 takes the place of face 1. And the same thing happens for this corner for 120 degree. And then again, if we rotate by 240 degrees, we get another configuration of these adjacent faces and these adjacent faces. And if we rotate by 360 degree, we end up with the same cube. So can you people understand these three types of rotations?
Yeah.
are indeed the fundamental possible ways of rotating a cube. And we have four possibilities here, and we have two possibilities here, and we have, wait a minute, and we have three possibilities here. So in total, if we compose all possibilities, we have 4 times 2 times 3, 24 possible rotations of the cube. And this actually forms a group called the uh, group of symmetries, I think, a group of rotations of a cube. Does anyone know of a group of cardinality 24? Can you quickly say any example you have learned recently?
S4.
Yes. So what happens is that this thing is isomorphic to S4. Was this told to you in the first session? Was it claimed? Okay, perhaps not. So you can try and prove, if possible, that this group of rotations is indeed isomorphic to S4. And one more thing to note here is that this is a group. Are you convinced with that? Like, if we compose two rotations, we'll get a rotation. If we have a rotation, we can find the inverse of the rotation. And we obviously have the identity rotation. Okay, so let us solve that problem now. So first, the identity rotation. What is the fix of this? What is the number of fixed elements of this? Can anyone say? But before that, we need to know, means what are we fixing? I mean, what is the set A? The set A here is all those n to the power 6 possible configurations. So what are the number of configuration fixed by the element 1? It's a very trivial question.
Everything is fixed.
Right. So n to the power 6. Now consider the rotation 1. Rotation 1. There were 90 degrees, 180 degrees, and 270 degrees. I mean, and 360 degrees, obviously, but there is no need of considering it because that's basically 1. Let us consider the 90 degree and 180 degree for 90 degree and 270 degree, because these two are identical in some way. Because 90 degree, I mean, we are rotating by fixing a convention that either clockwise or anti-clockwise, and 270 degrees, just if we rotate clockwise, then this is 90 degree anti-clockwise. So these two are basically similar looking things. So let us say call it G1 and G2. And suppose we have this type of configuration of a cube, and the top face is say 1 and the bottom face is 6. And we are rotating about this normal to the top face 1 and normal to the bottom face 6. We are rotating by 90 degrees. If we rotate by 90 degrees, what happens is that these two adjacent faces, I mean, if we have these faces 2, 3, 4, and 5, these are the faces, right? The adjacent laterally placed faces. These 4 alternate. I mean, 2 goes to 3, 3 goes to 4, and 4 goes to 5. But 1 and 6 remain fixed. So convince with this.
Yeah.
So the top face 1 and the bottom face 6 can have any colors, right? So 1 can be colored n ways, 6 can be colored n ways. We have n square possible ways of coloring the top and bottom faces, because then they need not be of same color because they are not changing in this action. But all the lateral faces have to have the same color if we are planning to fix it, because 2 goes to 3, then 2 and 3 have the same color, because 3 was already in that place. Now 2 is in that place, so they two have to be the same color. 3 goes to 4, these two have to be the same color. 4 goes to 5, 4 and 5 has to be of the same color. So 2, 3, 4 and 5 have to be of the same color. and that color can be chosen in n ways. So we have n cube number of ways of having this done if we are rotating by 90 degree. And similarly, you can also see if we are rotating by 270 degrees, we have n cube number of cubes that we are fixing. For a fixed cube, I mean, by fixed, I mean the top and bottom faces are, I mean, we are fixing 1 and 6 to be the top and bottom faces. Then we are counting this. Is it clear with everyone? Or
Yes,
should I
it's fine.
repeat?
It's fine, I think.
Okay, so I hope everyone is understanding this counting. And this 1 and 6, by fixing 1 and 6, we're getting n cube number of ways. And this 1 and 6 are opposite faces. And what are the possible number of opposite faces? We have 3 opposite faces, like 1, 6, and 2, 5, and 3, 4. And each of them can take these places, the top and the bottom place. And our axis remains fixed because that's how we have defined the rotation. So there are 3 possible ways of doing this, and in each possible way we have n cube number of ways. So in total we have 3 times n cube number of ways for 90 degree, and the same for 270 degree. So in total we have 6 times n cube number of ways for 90 degree and 270 degree. So I hope it's clear, this calculation for rotation. Rotation 1 only, we have left 180 degree. We'll do this in the next slide. So if anyone wants me to repeat anything, you can say. Okay, so let me move on. Now rotation 1, 180 degrees. Rotation 1, 180 degrees. Can anyone tell me, similar to the previous calculation, can anyone tell me how to find the number of cubes fixed after we have done this action? It is very similar to what we have done previously.
Is it 3n to the power 4?
Could you elaborate on each of these steps?
Sir, because when rotating by 180 degrees, only the 2 opposite sides have to be the same. Not every side has to be the same. So for choosing 1 and 6, we have n squared options already. Choosing
Yes.
2, 4, 5, 2, 3, 4, 5, now we get 2 choices. So it's n and n. So then we have n to the power 4 choices.
Right. And
But then,
3 is coming because we have 3 possible ways of choosing 1 and 6. Means the top
yes,
and
sir.
bottom. So
Yes,
there
sir,
are
but
3 into the...
I had a question because
Yes.
oh no, it's okay, okay, sir. It's okay, sir.
Okay. So this is 3 into the 4, and next we move to rotation 2. I think this is the edge, and in edge we have only 180 degrees. So what happens in this case is that, as I had already mentioned, the adjacent faces, I mean, one edge is formed if we have this one face here and one face here, right? What happens is that as we rotate by 180 degree holding this edge, then these 2 faces get interchanged. And similarly, we have another edge in the bottom. So there will be face here and some face here, say. And these 2 faces will get interchanged. And if we see, what happens is that the lateral faces also gets interchanged in this process. Means you can't always it is impossible to interchange the top faces and top 2 adjacent and bottom 2 without interchanging the lateral. So what happens is that these 2 interchange, these 2 interchange, and these 2 interchange. And we have 6 possible ways of choosing these 2 edges. 6 because you can take a cube and say for the top two opposite faces, we choose this edge and this edge, one possibility, this edge and this edge. Similarly, this is for one pair of opposite faces, we choose two edges, and similarly for each of those opposite faces, we choose two each. So 2 plus 2 plus 2. So six possible edges. So now total we have six possible pair of edges that we are holding and rotating. Consider one such pair and rotate and tell me what is the number of configurations fixed by that action.
In cube.
Yes, NQ.
Right. So I think you can clearly see these things. So it is 6 times n cube, and then I think we have one more rotation left. It is rotation by rotation 3, say. That is, it has 120 degrees and 240 degrees. We're not writing 360 degrees because we have already covered the identity element. So for rotation 3, can anyone prompt if anyone has calculated already? Otherwise, we'll move on to calculate. 120 and 240 degrees, we can calculate for 120 and 240, it will be same because it is just anti-clockwise of 120 degree. Or you people may try for some 2-3 minutes and then tell me. It is very similar to what we have already done.
Is it n square for one particular corner?
4n square in total.
Yes, 4n square in total for, the 4 is clear, and n square for one corner because the 3 of the adjacent faces have to have the same color and the 3 of the opposite adjacent faces have to have the same color. So n in times n. And is it clear to everyone apart from those who answered?
Yes.
Okay. So we get 4n square for 120 degrees and 240 degrees also 4n square. In total, we have 8n square. Do we have any other rotations left? We have completed identity, rotation 1, rotation 2, and rotation 3. And we have found all the possible fixed elements by each of these elements from the group of 24 elements, that is S4. Why it is S4, that one you have to try and check, but we don't need it to be S4 in this proof. It can be any group with 24 elements having the properties that we said. And we had already proved that the number of orbits k is sum of fix g varying over g divided by cardinality of g. And if we apply this to our question, then we get n to the power 6 for the identity element, then 6n cubed, I think, for the 90 degree and 270, then 3n to the power 4 for the 180 degree, then 6n cube. Correct me if I am writing any wrong thing. This 6n cube is for the edge, and lastly 8n square by 24. This is the number of orbits, and you can clearly see that this number, this total number of orbits, represents the total number of distinct configuration. Because if we have one orbit, say this one orbit and one element here A, then you can reach by rotation to every element here B. And any other orbit has to be distinct with A. Like C, you can't reach C from A, because if you reach, then this two has to be one orbit. So we have calculated the total number of distinct configuration after coloring it with n colors, and this turns out to be this formula. So this is one of the applications of what we had proved. We have proved this result, that K is summation stabilizer of A by this, and This is called Bonsai's lemma. And one thing that is very that comes to mind is that this is a relatively simpler question. We do not need to derive so many things, so many definitions, and to prove a simple question of combinatorics. The thing is that Bonsai's lemma has uh, much more applications to combinatorics and much more complicated problems. Where here it was relatively simple because we did not have any restrictions with colors. The cube was, I mean, the rotations were easily, you could write all the possible rotations explicitly and so on. What you can do, if possible, is read on this thing called Paulia's uh, theory of counting, which somewhat extends this lemma. And you can understand it at this level after you have understood all these things told today, would extend this one-size lemma to much more complicated problems, and it leads to various useful theorems that you can readily apply if we are given such combinatorial problems. So this thing I wanted to tell about this problem. Now we go on to some more useful applications of group action, and we'll apply group action to prove some things in group theory itself. We don't need to move on to other subjects of mathematics like combinatorics. We prove something useful in group theory. Okay, take any group G, and cardinality of G is say n. Okay, and you consider this set S, set consisting of x1, x2, xp, such that x1, x2, xp, this product is equal to 1. So clearly this set is non-empty because, okay, one thing to note here is this is an ordered, tuple, and equality is given by like x1, x2. Suppose p equals 2, then x1, x2 equals y1, y2. If x1 equals y1 and x2 equals y2. Okay, so clearly this set is non-empty. You can see the set E, that is, 1, 1 belongs to S. Can anyone tell me the cardinality of this set? What is the total number of p tuples? And p is here any prime, but we actually don't need it to be prime at this moment. We'll require it later, but let it be p any prime.
And the xi are integers.
No, these are okay. I should have mentioned this xi belongs to G.
Oh, and one is just the identity.
And one is the identity of G.
Okay.
So try to find the cardinality of this set S. What is cardinality S? This is basically counting. You have to use the property that x1 to xp multiplied gives 1, and you have to find the total number of elements in S. And the order of the group is, when the cardinality of the group is G. N itself. Has anyone any idea the approach, how to count it? Suppose, okay, are people trying or should I start to tell?
I think you should.
Okay. I will not tell the entire answer. I will. You will only say. I'll just give some hints, and you will start saying. I think uh, x1 to xp. We have this ordered tuple, and x1 can be chosen in n ways, right? Do you have any restriction to x1?
No.
Similarly, x2 and up to x up to say 1 minute up to say x1 x2 xp minus 1. All these things can be chosen in n ways, or do you have any restriction to that? Up to p minus 1.
No, we don't.
Yes, it could be chosen in n ways only.
Yeah, each of them can be chosen in n ways. Then we have xp, and xp has to be, and if we have chosen x1 to xp minus 1, then xp has to be the inverse of x1 x2 xp minus 1, right?
Yeah.
And inverse is unique, you know that. So
Yeah.
this has to be this is fixed after we have chosen x1 to xp minus 1. So this is chosen in only one way, and each of these x1 x2 can be chosen in n ways. So we have n to the power p minus 1 ways of choosing. So in total we have n to the power p minus 1 as the cardinality of this set S. So are you people convinced with this?
Yes, sir.
Everyone, I think.
Yes.
Okay. So we'll be proving actually a very beautiful theorem using this approach, and the thing is that that theorem can be proven in other ways without using any such means counting methods. But this is very this looks beautiful. Okay, so
I have one question.
yes. In this slide,
No, in the question on the rotations of the cube, can we solve the problem using properties of groups instead of drawing the diagrams? I mean, is there an abstract solution using just the
I
properties of
mean,
S4 like that?
we use the properties of S4, but see, if we are using, okay, there may be other approaches, but the approach I have used, we are using that fixed G, right? The summation fixed G by order of G. But to find fixed G, we need to know about, the all possible, the set we are acting on, right? Otherwise, how to say which are the fixed elements?
Yes, I was thinking if we proceed from cube to larger polyhedra, then it will be extremely difficult to visualize the things. So what we do?
Right. For that, you have, for a larger polyhedra, you need not get S4, you will get different, complicated larger groups. But for that, you have other techniques of counting that I think if you go and read the Paulia theory of counting that I have mentioned, you will know about what things we can do if if we are in a different context. So I will suggest that you read Paulia theory of counting, which will be very accessible to you because you have understood today's session.
Okay, thanks.
And in there also we that is also the Paulia theory of counting also has disadvantages. Like there is something called if I remember correctly, class index or something. I don't remember, class index or some other index. So that thing also has to be after you have calculated that thing, you can solve these type of problems. But the calculating that thing also needs some some labor. It is not as easy as we solve other things in group theory. Not that abstract, but after you have calculated certain things, you can apply it to any type of problem. And what happens is that many different problems correspond to the same group. So after you have found some things of the group, you can apply it to different contexts. But to find that thing for the group, you need some labor. That one you can read in that Paulia theory of counting. Okay, so where was I? Okay, we found this set S as cardinality n to the power p minus 1. Okay, so do you people know about this group? You know about Z mod NZ, right?
Yeah.
Yes, sir.
Yes. So this has cardinality p, and under addition I'm considering. Under multiplication, what is this cardinality?
P minus 1.
Right? So
What? It's not a group under multiplication.
exactly, we have to exclude 0. And after that we find the cardinality. I mean, if P is a prime, then only it is a multiplicative group. And I have mentioned, I think it's a prime. Like, I mean, if you take any prime and then you consider this 0, 1, P minus 1. And if you exclude this 0, then this set forms a group, and that is the Z mod PZ. It forms a group under multiplication, and we are now considering under addition. So is it fine now? This group Z mod PZ.
That's not
You
Z
know it's a
mod
group.
PZ. As soon as you exclude the 0, it becomes Z mod PZ star. So invertible elements in Z mod PZ.
Okay. I mean, I was referring to that. Okay, fine. So Z mod PZ is this, and if we consider all the invertible elements, we consider it is called Z mod PZ star. Okay, this is a group under multiplication, and we are presently considering Z mod PZ, and it has cardinality P. Say it has cardinality P, and we are letting this group act on this set S. I mean, we are considering the action of Z mod PZ on S. So to define an action, we need to define the product between G and say X, and this X is X1, X2. So let us define it in this way. Clearly 0 and X give X, because that is the definition of action. The identity element should map the thing to itself. And suppose we have 1 here and we multiply with X, then let it be this X2, X3, X1. So it is cyclically permuting things. If we take 1 plus 1, X, and we define this in this manner. I mean, we are free to define action, and we have to check whether it's an action or not. So one thing is to check is that this is indeed an action. Like if we have, say, up to all the elements in Z mod PZ, we can write, say, R times X. R belongs to, say, Z mod PZ. And then if we have 2, then 2 is in the end. So if R is there, then say XR plus 1 and X1 XR. I think this will be, because if you 2, then yeah. And then if you have any other element in say T belongs to Z mod PZ, then wait a minute. Then T times R of X is having X T times R plus 1. Then last is XTR. And if we have, say, what do we have? Rx XR plus 1 XR, and then we operate operate with T. It is moving it. Okay, this is
should
not
be
T
T
plus
plus
R.
R.
T plus R, right. I was also confused why. This is T plus R because we are under doing the addition. Then as we operate T and R of X, then clearly you can see this will move T times. This is T plus R. And this will be R plus 1 plus T. And this will be X R plus T. And this shows there's indeed an action because we can write R of T of X, R of T of X, and identity maps X to X. Okay, so after we have got an action, what we get is that for every element we get equivalence classes because action leads to an equivalence class. For every element we get some orbit of X. An orbit of X into stabilizer of say, X is order of group, and here order of group is not this. I mean, our order of group is Z mod PZ because this is the group we are using to act on S. We initially had a group G, but we are not using it anywhere at this point of time, and it is P. So this orbit of X for any element X has to divide this prime P. So it can be 1 or P. If orbit of X is 1, cardinality of orbit of X is 1, then X1, X2 up to XP, any permutation of it gives the same X1 to XP, which implies X1 equals X2 equals XP. And let us say it is some Y. So if orbit of X equals 1, then X equals Y. All the same elements. And can anyone give me a very trivial example when orbit of X equals 1? For which X?
All ones is a possibility.
Yeah, all ones is a possibility. And means we don't know much about the group G, so we can't take any Y belongs to G and consider the tuple because we don't know what group G is actually. So and we can consider this tuple and this as this is the orbit of cardinality 1, but this S is partitioned into orbits, right? Say union of orbits, not cardinality. And cardinality of S we have found to be n to the power p minus 1. And say we had orbit size of X has to be 1 or p. If orb X is 1, then X is a fixed element, right? Because all permutations, cyclic permutation give the same element. So if orb X is 1, X is a fixed element. So if number of fixed elements, say we call it F, then total number of fixed elements orbits, I mean the orbits of cardinality 1, the total cardinality is F because every fixed element gives an orbit of cardinality 1. And suppose total we have F fixed elements, then we have F orbits and each of cardinality 1, then we have the cardinality F. Apart from that, what are the possible orbits? The orbit of X can be P. So n to the power P minus 1, this cardinality of set S, is sum of this, how to write it? I mean, the P-sized orbits plus F. Are you people convinced with this equation, this last equation?
No.
You take any element x, and if orbit of x equals 1, then the element x is a fixed element. Are you convinced with this? I mean, we proved in the last slide, if orbit of x equals 1, then if you permute, I mean, this is nothing to see actually. If orbit of x equal to 1, then x goes to x, means all the elements lead to x itself after applying on x. So if orbit of x equal to 1, orbit of x is, if we take any element from z mod pz, apply it on x, all the possible elements that we get, we collect them, and that is the orbit. And if orbit of x has cardinality 1, then we are getting only x after applying all the elements from z mod pz. So x has to be a fixed element. Is it
Yes,
fine
it's
now?
fine.
Okay. Now suppose we have f number of fixed elements. If we have f number of fixed elements, then what is the sum of the cardinality of those orbits? Each has size 1, so total we have size f. Total size of orbits of fixed elements. Fine with this? Is this fine, this f thing? Or should I repeat it?
Yeah, it's fine.
Okay, I hope it's fine with all.
So can I repeat it once?
Yes. See, this thing is clear, right? If we have orbit of x equals 1, then it has to be a fixed element. And if fixed element, then orbit of x equals 1. Then
Yes, sir.
consider all those fixed elements. Say x and y are two fixed elements. Suppose only two fixed elements. Then orbit of x and orbit of y each have size 1. Then total size is 1 plus 1. And that's what I'm telling this thing. The
Okay.
total number of elements which are fixed is equal to the total size of the... Yes. So we have two types of orbits. One is this orbit of x equals 1. Another type of orbit is orbit of x equals p. This is because orbit of x has to divide the order of z mod pz, and order of z mod pz is p. So it can be 1 or p. And we have considered all those possible ones, that is f. So if we exclude, I mean, if we write n to the power p minus 1, we can write it as f plus the cardinality of this p-sized orbits, right?
Yes, sir.
Because of orbits partition S, then sum of their cardinality will be the cardinality of S, and each cardinality can be either p or 1. And if it is 1, then just count the number of elements because it is 1 only. And if it is p, then it is the p times something. I'm writing it again for clarity. We have cardinality of S is sum of cardinality of orbit, say I equals some 1 to k, suppose. We are in the finite setup, everything is finite here. And this is same as sum of 1, I equals 1 to f. If you remember, this f is number of fixed elements, plus p times something. Is it fine with all? This last equation.
Okay.
Okay. With everyone, or should I repeat it again because we'll use it to prove something?
Yes, sir. It's okay.
Okay. So this is f plus p times something. And we had s here, and s equals n to the power p minus 1. Okay, up to now, have we used anything related to n? N was the size of group, okay? The original group about which we have no idea, any abstract thing. Have we used anything related to n up to now?
No.
Exactly. So this thing is true for any group because, I mean, this is only just a symbol I have used. So I will use something related to n now, but up to this thing is a general result. And the good thing about this is that the theorem I am going to prove here, I will use something related to n, but you can use this thing for proving other theorems, other results that are much more useful, because this is a general for any general group. One thing you can do, you can try proving Fermat's Little theorem using this result. I mean, you have many proofs for Fermat's Little theorem, but try using group theory. Okay, so let's move on to the present thing. What I'm doing up to this, everything is clear. Now assume that this same p divides n. The same p divides n. Okay, then we had n to the power p minus 1 congruent to f mod p, and this p divides n. So what can we conclude? What can you conclude about f?
P divides
Can
n.
f be one? Can f be 1?
No.
No.
Clearly no, because p divides n. And okay, we had an example of a fixed element. Do you remember this? I mean, not e, this element. This was a fixed element. So we have more than one fixed elements, because f can't be 1. If f is equal to 1, we arrive at a contradiction. So we have more than one fixed element. So there is another element, say x, 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 and x is not equal to 1. And this belongs to S because we have a fixed element in S. So is it fine with all this thing?
Yes, sir.
Yes.
So this fixed element belongs to S. What does that mean? X to the power p equals 1. Because this is a p tuple. And p is a prime. So order of x equals p. In this step, I mean, this implies this. Has anyone any question?
No.
Okay, can this, suppose I write x to the power 6 equals 1. Does that imply order of x equals 6?
No, sir. It could be 1, 2, 3, or 6.
Fine, fine. So these things are clear to everyone, right? These ideas.
Yeah.
Yes, sir.
Okay, fine. So clearly you get that order of x equals p. And we started with a general group. We added the restriction that p divides the order of group, which is n. Then we get there exists some element x belongs to the group such that order of x equals p. This is called Cauchy's theorem. And this is very, very useful theorem because every time you get a group G and you know the order of the group, you get the prime factorization of the group. For every prime, you get an element. And after you have got an element of order P, you can consider the cyclic subgroup, right? Of this group. Are you people aware with cyclic subgroups?
Yeah.
Yes, sir.
Yeah. So you can always construct a cyclic subgroup using this idea every time you get a group. So this will be required in some proofs in the next and the last talk. So this is a very useful theorem, and the good thing about it is that we proved this using group actions. So anywhere in this proof, when we started with defining S, it did not seem that we are going to get this result. So most of the time, what group action does is that we cleverly define a set and we choose a suitable group and act it on that set, thinking of the end result. I mean, it's like going backwards. If we know the end result, then we can construct such a group, we can construct such a set and apply group actions. After applying group actions, we can use all those orbit stabilizer theorems and the one side's lemma, many things that we proved in general for group actions. So this is basically a way in which group actions work. Okay, so when we defined group actions, we wrote G cross A to a map, but A can be any set. So what is the most obvious thing that A can be? Anything that
The
makes
group
it easy?
itself.
Yeah, the group itself, because we have already defined the product of G1 and G2 in the group. So we don't need to define this product again. It's already defined. So action is already defined. And one thing to note is here, when G acts on, G acts on itself, we get a map from G cross G to G, and every element G belongs to G permutes the elements in G. Okay, one question: does there exist G belongs to G such that G times X equals X for all X? Obviously, that does not exist apart from G equals 1, right? So even one more thing is that even for any X, Gx is never equal to X if G is not equal to 1, because we are considering X belongs to G. Okay, so keeping these things in mind, will define something. You, as you said initially, you people know about the group SA, and similarly, you can consider the group SG when A equals G. For every group element G, you get a function phi G that belongs to SA. Is it fine? This, how we get a function, is it fine as per the definition?
What's the function definition?
Exactly. The function is basically what we have done here. That is we take a G and we get a function phi G, and the phi G is defined in this manner. Phi G of A is GA, because we have defined this GA, right? Because we have got an action. So for every G, we get a phi G. And phi G inverse of A is G inverse A. This is the function. So are you people able to understand these functions are mapping G to G? This phi G and phi G inverse are mapping G to G.
Yes, sir.
Okay. And one thing to note, this phi G inverse and phi G are inverse functions of each other. Can you see that clearly?
Yes, it's clear.
Yeah. So all these functions have inverses. That implies that this belongs to SA, because SA is the set of all bijective functions. Now we consider this map from G to SG. The map is defined by G is mapped to phi G. Suppose G1 and G2, we have G1 and G2. Then the product G1, G2 in G is mapped to phi G1, G2. Now phi of G1, G2 of A is G1. Okay, before proceeding, how is, this is a group, right? So how is the product defined here?
Composition of functions.
Yes, composition. So this is phi of G1, G2 of A is G1 of G2A. And this is basically phi G1 of G2A. Phi G1 of phi G2A. So this G1, G2 is mapped to phi G1, phi G2. When phi G1 times phi G2. So what does this imply? And obviously identity is mapped to the identity function. I mean, how to write it? Phi 1, the identity mapping. So what does this imply? The product here is mapped to the product here.
This map is a homomorphism.
Yes. So this map gives us a homomorphism from G to SG. And one thing to see is that even if we did not have G here and any set A, any normal set, then also we'll get this. I mean, then also this is G2 times A is some G2 dot A we write, and G1 dot G2, and we know that G1 dot G2 is G1 G2 dot A. So this equality is valid. So for this thing to work, we have just used a G2, and when G and A, there is a product defined between them. We have nowhere used that this is a group. I mean, this is a group. I mean, A is a group we have nowhere used. We have used a G is a group, but G is acting on A. A is a group we have nowhere used, even though we have written it as G, but we have nowhere used in the proof. Because even if it was a normal, any random set, then we would have the product defined. And this product also defined. And G1, G2 of A, like G1, G2 of A is G1 of G2A. This is by the definition of action. So any capital A would work up to this homomorphism. Is it fine? Or should I repeat anything that any G argument that I have used here?
It's okay for me.
Okay. So I think I should repeat, otherwise there will be problem afterwards. If there is a set, say G cross A to A, where I'm having an action, and we have G dot A, that is the product, and we have G1 dot G2A as G1 G2 dot A. And this time also G1 is mapping to some phi G1, right? Because phi G1 is anyway a permutation of A. And phi G1 of phi G2 of A is G1 of G2A is G1 G2 of A. So this G1 G2 is mapping to this thing, product of these two things. So irrespective of whether this A is a group or for any structure to it, this homomorphism from G to SA is always true. I hope it's fine
Yes.
now.
Yes, it's fine.
Yes, sir, it's okay.
Okay, so every time we have got a homomorphism, it's very natural to ask the kernel of the homomorphism, the range of the homomorphism. Have you people heard, if you have read the isomorphism theorems, then you know about the kernel? Can anyone define the
Yes, sir.
kernel? Can anyone define the kernel? And find the kernel when A equal to G, what is the kernel?
If A equal to G, the kernel is the ident. I'm sorry.
Yes.
Sorry. Just a
That's the
second.
identity. It's okay.
Yeah, it's an identity because kernel is that element which fixes everything. I mean, kernel has those elements which fix everything. And if you have A equal to G, then you can't have any other element fixing everything, as we have seen before. One thing to note here, suppose A is any set, can you people see that kernel is equal to intersection of stabilizer of A belongs to A? Is it visible? I mean, is it very obvious?
Because it must fix everything, maybe that's the definition.
Yes, kernel fixes everything, and stabilizer of A fixes A. Then if you keep on taking the intersection, then it will fix everything. I mean, fix every A belongs to A. That is basically kernel. Okay, for our purpose, we have kernel equal to the set, that is only the identity. Okay, so by the first, okay, anyone say me the first isomorphism theorem? What is the first isomorphism theorem? I mean, I think it was in the last class.
G mod curve phi is isomorphic to im of phi.
Right. So G mod curve phi is isomorphic to image of phi. So what is G mod curve phi in this case?
G itself.
Yes. So G is isomorphic to some image of phi, and image of phi is a subgroup of SG. Is it a subgroup? I mean, have you people ever tried proving if image of a homomorphism is a subgroup of the codomain? I mean, yeah, this image is a
Yes,
subgroup.
Yes.
sir. Yes.
Okay. So after we have got isomorphism, we can say that we can identify G as a subgroup. We can identify G as a subgroup of SG. And when G is finite order, then G is basically a subgroup of Sn, right? I mean, G has an isomorphic copy, which is a subgroup of Sn. So studying Sn is studying all the finite groups. Because if we study Sn, we study all the subgroups of Sn, and that is equal to studying all the finite groups, because finite groups are basically the subgroups of Sn, right? So this thing, so are you people clear with this? I mean, if you study any group which has finite order, then it has to be a subgroup of Sn. It has to have an isomorphic copy. So if you study the isomorphic image, that is this thing, then you study the group. So after you have studied Sn completely, you have studied all the finite groups, all possible finite groups.
Yes, it is clear.
And this thing is called the Cayley's theorem. And I think you have heard about this Cayley's theorem in the first class. I mean, not in a rigorous manner. Cayley diagrams and all. Uh, okay, this is the Cayley's theorem, which says every group is isomorphic to some subgroup of Sn. That is the image of this homomorphism. And one more thing, need it be a proper subgroup? I mean, can it be equal to Sn? I mean, we have nowhere said, we have nowhere answered this thing. I mean, is this inclusion proper, or is it equal to SG? Most of the times, what happens is that it is a proper subgroup. Like, do you people know Dihedral group is isomorphic to S3? Have you people proven this or heard of this?
Probably it was the material of the previous lecture.
Okay. So try to prove this thing using actions. But clearly D8 is not isomorphic to S4 because cardinality is already very different. But D8 sits as a subgroup of S4. So most of the times what happens is it's actually proper inclusion and not isomorphism to the codomain. Okay, so let's move on to the next thing. So up to now we have seen actions of a set G of a group G on a set A, and for a group G on a set on the same group itself, we have seen the action by multiplication of the element by left. I mean the product defined as before. So as I have already said, is that the action need not be unique, right? So G dot A can be defined in many ways. Defined in many ways. Another way of defining is G dot A equals G A G inverse, which is called conjugation. I mean, here A belongs to G. Otherwise, what is the meaning of multiplying in right? Because only left is defined before. So this A belongs to G, and GA G inverse is an action of G on G itself, and the product is defined in this manner: GA G inverse. So one thing to check is that it is indeed an action. I mean, it is also very clear from the definition because the element. Okay, so with every action, we have an associated orbit. Orbits of every G and stabilizers. Can anyone tell me what is the stabilizer of an element under this action? What is stabilizer A? Stabilizer A is that G such that GA G inverse equals A. So the clear thing that we get is that G such that G equal to a G. Have you people heard of centralizers before in this sessions?
Yes, sir. It was in the second lecture.
Yeah.
And this is basically the centralizer of A, right? All those things that commute with A.
Yes.
And we have got stabilizer of A equals centralizer of A. Let us write it CA. Okay, if okay, one thing, the stabilizer is a subgroup, right? We have proven it for any action. So we don't need to show that centralizer is a subgroup. I mean, you can prove it in your own methods, but we have already proven that stabilizer is a subgroup. And we have proven that G mod stabilizer, that is the index of the subgroup stabilizer is equal to the size of the orbit of A. This was basically the orbit stabilizer theorem, because this can be written as mod G by mod stabilizer of A, then we can prove the orbit stabilizer theorem. And we know that orbits partition the set, and this equals sum of orbit. Which means sum of okay. And one thing to note here is that have you guys heard of the center of a group? If you have heard centralizers, if you must have heard center.
Yeah.
Yeah. So if A belongs to center of the group that I note by Z, then GA G inverse, this action leads A. I mean, the orbit of A has only cardinality 1, because any G you take, it commutes and we get A. So in this equation, if we split the summation into, that is summation A belongs to G, sum of G stab A can be split into summation A belongs to Z, this G stab A, plus summation A does not belong to Z, G stab A. If A belongs to Z, we know that G stab A is basically orbit of A, and orbit of A has cardinality 1. So this is the cardinality of the center. This thing. Clear? Because G stab A has cardinality 1, as proven before in the last slide. And this thing is summation A does not belongs to Z, G stab A. And stab A we can write centralizer of A, because we have proven that stabilizer of A is centralizer. And this was here the cardinality of the group. Is this derivation clear to all?
Yes.
Yeah.
Yeah, this is just basically applying the orbit stabilizer theorem to a particular action. So this is called the class equation. and this is very useful in proving some results that will appear in your final and next talk. But we'll be proving a very simpler result now, and that would probably be the last thing that we'll do today. Suppose order of a group is p to the power n, and p is a prime. What can we say about center? What can we say about order of center? Any quick answers? Using the class equation that we proved. I'm writing the class equation again because we will need it. Using the class equation and Lagrange's theorem that we proved before. What can you say about the order of center?
The last term, was there not a summation?
Yeah, summation.
So it will be a multiple of p at least.
Exactly, because this is a multiple of p, and these are all divisors of p to the power n by Lagrange's theorem. So this entire thing is a multiple of p. So this has to be a multiple of p. And if this is a multiple of p, clearly the center is not equal to 1. So we have a non-trivial center. This is a non-trivial center. And have you guys proved that the center is a normal subgroup? Have you proven it? The center is a normal subgroup.
No, sir, we haven't proven, but I think it's trivial to do. It's not very difficult.
Yeah, it's very trivial, and this is one way of saying that this group G has a normal subgroup if it has order p to the power n. And this is very useful because we'll be studying a class of groups called uh, simple groups, which don't have any normal subgroups, and that will be mostly the material in the last lecture. And mostly the trick used is to bring out the center, because that is one of the known normal subgroups. And one more thing that I wanted to mention is that suppose you have a group G and H is a subgroup of G and index of H is say 2. What can you say about H? Index of H is G, means there are only two opposites, H and suppose say A times H. A belongs to H. What can we say about H? Can we say that H is normal? Is it very obvious? Is it visible to you?
Yes, because we take an
To
element
prove it is
outside.
normal, we have to show. Yeah.
Just we
Element,
take
say B outside.
the outside H and outside H, then the left and the right quadrant must be the same thing.
Yeah, because we have partitioned the group into H and AH, and also we have partitioned it into H and HA. So this two has to be same. This proves H is normal, but can we extend this? This lemma. If we have order of group is n and P is the smallest prime dividing n, and index of H is P, is H normal? This is something you can try. This this is something you can prove using basic ideas, not even group actions, but it would be very interesting if you try using group actions. You can try this after the session. And the great thing about it is that this was solved by some mathematician when he was at our age. I mean, he was an undergraduate, and he only posed this problem and he himself solved it. And you can find this problem in most of the textbooks. If G is a group of order n and P is the smallest prime dividing n, then if H is a group of index P, we have H is normal to G. And this is very useful because it helps us in finding the normal subgroups. I mean, if we know this thing. And one last thing that I wanted to mention before ending is that normal subgroups, you had AH equals HA for all. In abelian groups, what are the normal subgroups?
Every
You know
subgroup,
about abelian
Any
groups, right?
subgroup.
Yeah. In abelian group, every subgroup is normal subgroup. In abelian group, what is this? Suppose we take an element and we keep on conjugating with G. G belongs to G. What is this thing? This set for all G. This set. In case of an abelian group, what is it?
It
Eight
is itself.
set of eight.
The element itself.
Yeah.
Exactly, the element itself. So the reason we, define these things and these things is like not being abelian, but trying to be as close as possible to abelian. I mean, AH equals HA. This is looking like some commutative relation, but commutative as sets because not element wise. Similarly, you can prove if this set is called some CA, then some KCA equals CAK. And this is also, I mean, reaching abelian as close as possible. The purpose is that because after we have understood abelian groups, we try to generalize to non-abelian groups, and we define analogous things that reach us, just take us more closer to the abelian groups. I mean, after we have after defining element-wise commutativity, the next thing that comes to mind is subset-wise commutativity. Then subset, we know subgroups. Subgroups are some better subsets because they have some structure. And then if we define their commutativity, we get normal subgroups. And another advantage of defining this conjugacy thing is that, say G inverse, what is the order of this element? Or some A, what is the order of this element? You can show that this has order equal to order of A. So basically what is happening is that we are looking at A, but in a different context here. If we take this example of equilateral triangle 1, 2, and 3, and if we take the rotation R by 120 degrees and rotation R, let's say R square by 240 degrees, and if we rotate it by 120 degrees, okay, this is 1, 2, and 3 in this manner. If you clockwise rotation, okay, so if you rotate by 120 degrees, say, then we get this thing, 3, 2, 1, and there is a reflection also. Now try to conjugate R with S, like S R S inverse, and try seeing what we get. If we take S inverse first, then we're reflecting this thing because S inverse is basically S. Then we're getting this triangle 1, 2, and 3. Then we do R, then we get 2, 1, and 3. And then we do S again. Then we get 2, 1, 3. And we started with this is SR S inverse, and this thing is basically doing R square because 1, 2, 3 we had, and if we do R square, 1 will come to here, then come to here. This 1, 2 will go to this place, This go to this place. So R square and R are related as conjugates. And if you see closely, R and R square are not two very different things. That's just clockwise and anti-clockwise. So we are just seeing R in a different way, and then we get R square. I mean, if we reflect, then that is basically seeing it in anti-clockwise direction. So that is mostly the idea of the motivation for conjugates. And one thing I forgot to mention, this is called the conjugacy class of a conjugacy class. And I think that's all that I had to explain today. You can look up Paulia's counting theory and try the problem that I said, if P is the smallest prime dividing n, that problem. And if you have any doubts, you can ask now.
Is Damit and Foot a good book for these things?
Yes, after you have understood the basic motivation for it, you can follow Damit and Foot. And one or two terms that I did not mention, let me write it, like faithful action. Is that action whose kernel is identity? That thing is called a faithful action. And one more thing is called transitive action. And it has only one orbit. And that is, I mean, we know that this is union of orbits, right? So here only one orbit. So this is itself one orbit, say O1. It's one orbit. This is called a transitive action. And you can see that the action of group G on itself is a transitive action and a faithful action. So I think that's all. Any other questions? Okay, if not, I think we should end it.
Thanks, Dada. It was a great lecture.
Yeah, it was really good.
Thank you so much.
Okay, I hope you understood the things and you'll use it. Okay. So Venkat, you can end it.
Yeah, man. Thank you for the talk. I'll end the meeting.
Yeah.